day and welcome everyone. Today what we're going to be talking about is what are the definitions of acids and bases. There are actually three different definitions of acids and bases, and so one is going to start us off with what in general is an acid, and almost always the definition of an acid is going to be the same. I want you always to think about what acids do you know, like hydrochloric acid, like sulfuric acid, like nitric acid, like acetic acid or vinegar, right? So if you think about some of those ones that you already know, sometimes that helps. And writing the formula is going to help even more. So I know that I have things like hydrochloric acid, which is like your stomach acid, for example, also used in pools, which might be called muriatic acid. We've got something like acetic acid, which is vinegar, HC2H3O2 or H2, CH3COO minus. And so we know that if you have something like sulfuric acid, H2SO4, which can be found in things like car batteries, we know that this hydrogen ion is very, very important when it comes to being an acid. So it's got to have this H, but it's not only that. It's not that it has the hydrogen ion. It's that when you put it in water, it's going to release hydrogen ions. So by the 1884 definition, which is this gentleman over here, Arrhenius, Svante Arrhenius, an acid is a substance that releases hydrogen ions in solution. H plus ions in solution. So hydrogen chloride, HCl in water solution ionizes. It becomes H plus and Cl minus. We know that. If that's the case, a base or an alkali, so they will use the word alkali, is a material that can donate hydroxide ions. So if we think about the bases that we know the strong ones. So they're any of the 1A's, so like if you have sodium hydroxide or lithium hydroxide or potassium hydroxide, so going down that first row of alkali metals, or also Caserba. Those are also going to be some of the strong bases, and those are the ones that are going to dissociate and break up into ions and release hydroxide. Sodium hydroxide in water solution becomes sodium ions and hydroxide ions. So we know that. We know that something like NaOH is going to break up, and it's going to give us Na plus and OH minus. And so by this definition, the base, Arrhenius base, is going to release hydroxide ions. Okay, now Bronsted, J.N. Bronsted, as well as Thomas Lowry, they worked independently, but both came up with this definition of acid base that's a little bit different, slightly different from Arrhenius's definition. Now the acid definition is very similar. The only difference is that instead of using hydrogen ion, they use proton, okay? An acid is a material that will donate, or that donates, a proton or multiple protons in solution. So then what's a base? Well, if the acid is donating the proton, the base is going to be accepting a proton. So now this definition of a base is very different because it doesn't say anything about hydroxide. And sometimes you don't even have the hydroxide ion that's present in there. So a base is a material that accepts or latches onto a proton or protons. I'm going to put kind of an apostrophe S in there. Okay, so the Bronsted-Lowry definition is definitely going to be broader. It includes some ideas that might not initially seem to be acid and base interactions. So you might look at it and say, but that doesn't look like a base, so I'm kind of confused. I see the acid, but I'm not really seeing the base. But as long as it's something that's going to accept the proton, then we're going to call it a Bronsted-Lowry base. It says, just as with the Arrhenius definition, all the familiar materials we call acids are also acids in Bronsted-Lowry. It's important to note that, this is what this chart is going to show us here, a strong acid yields a weak conjugate base and vice versa. We're going to talk about what these conjugates are, okay? So if we look at this chart, we're going to come back to it in just a little bit here. We can see some of the strong acids that we were talking about here. Hydrochloric, sulfuric, nitric acid are strong. Now, when you end up looking at what its conjugate is, and the conjugate is going to be on the other side, okay, of the equation. And the conjugate is going to be Cl minus, HSO4 minus, NO3 minus. And those are going to tend to be weaker, okay? If we go down the list, we're going to see that if we have a weak acid, so for example, I don't know, let's look at something like carbonic acid or something like hydrosulfuric acid, ammonia, so something like that, then so then we end up looking at the other side. So if you have a weak acid, it might end up yielding a weak base, but then at the very bottom, we can have our strong bases that actually are going to be like negligible acids. In other words, very, very, very weak acids, okay? So kind of good to know that whenever you have like a strong acid, you're gonna get a weak conjugate base or the other way around. All right, and now the final definition that we have is a Lewis acid and a Lewis base. Now, I am saying side note, and the reason why is because the College Board has actually removed the idea of Lewis from the AP exam, but it's always good to know as well. So this is also in 1923, and so this is the same Lewis as the Lewis dot diagrams. So for example, if you were to do a dot diagram of something like HCl, then you would have something like an H, and then you would have the Cl with all of the dots going around it. So that's our dot diagram. So what ends up happening is you might have something like NH3, ammonia, and ammonia is drawn as a pyramidal shape. It's got dots right up there. And so sometimes what you can do is you can look at a substance and either say it's going to be an electron pair donor or an electron pair acceptor. So by definition, acids, and this is a really, I'm not even kidding you, this is how I remember it, because sometimes I just need it real quick, and I'm like, somebody just asked me, and I'm like, oh, real fast, I know what it is. Acid starts with the two letters AC. Now, don't use this for the other two definitions. You would only use this for Lewis. And so acids are electron pair acceptors. So they're going to accept another one's electron pair, whereas bases are going to be electron pair donors, okay? And it's that simple. Again, we're not going to spend time on this, but if you see it in the text, that's what they're talking about with the Lewis acid base. Also, another big idea here is that water can either act as an acid or a base. And so what we say is we call it amphoteric. Please say the word amphoteric. Go. Okay, say it 3 times if you want. So what does it mean? Well, an amphoteric substance is going to be something that can act both as an acid or it can act as a base. So it can do both. So we know that water can either act an acid or a base. Why? Well, because if you look at water, it's H plus with an OH minus. There's your acid side, there's your base side, okay? And so this makes water something that is amphoteric. Now, if you see in the text, they're going to talk about amphiprotic, okay? An amphiprotic is a substance that can both accept and donate a proton or a hydrogen ion. So if it can both give one away or accept one, then it's called amphiprotic, okay? And so I'm going to show you an example of something that is amphiprotic as well. So we'll take a look at that in just a moment here. We're going to look at it when we look at some of the packet examples. Okay, so water can act as an acid or a base. So what ends up happening is if something is acting as an acid, we know that that means it's donating its hydrogen ion. Well, these are both water anyway, but you can check to see what its conjugate is. And so for every acid, you're going to have a conjugate base. And for every base, you are going to have a conjugate acid. So that's going to be your pair, okay? So the acid, I see, lost the hydrogen and became the conjugate base. The base, we know by definition, Bronsted-Lowry's definition, picks up hydrogen ions. And so we can see the conjugate acid is the one that has that hydrogen ion added in. Now, one of my tricks, too, in ensuring that I did this correctly is, I always say if you went backwards, your conjugate, it just means that it's on the product side. If you were to go backwards and reverse your reaction, your conjugate acid is still acting like an acid. What do acids do? Think about it for a second. They lose hydrogen ions. So look at what the hydronium ion is doing right here. If you look backwards, it lost its hydrogen ion and became a base. And if you look at the hydroxide, what do things that act as a base do? Well, a base will actually accept a hydrogen ion, so we can see that its acid, when it turns into the acid, it's gained that hydrogen ion back, okay? So that's kind of a nice way to do this. So let's take a look here. We've got a couple of acids and bases. We've got nitric acid, we know as HNO3, and then we've got water acting as the base, and you're always gonna have an acid with a base, okay? So what's gonna end up happening is the acid is gonna have its conjugate base that it's going to pair up with, and our base is going to have its conjugate acid that it's going to pair up with, okay? So when HNO3 loses its hydrogen ion, what does it become? Well, it becomes NO3 minus, so that would be the conjugate base. Now, the acid in this case, the conjugate acid in this case, is going to be the base accepting, Well, if that accepts it, it's going to become H3O+, which is the hydronium ion. Same thing for HCl with water here. So I'm going to end up losing my hydrogen ion. It's going to become Cl-, and the water then must be gaining it, which means I'm again going to get H3O+. So let's try some of these other ones. I want you to pause the video and let's see if you can answer these questions, and then let's come back and see how you did. Okay, so NH3 is a base. It's actually a weak base. And I can tell here because what ends up happening to it is it gained a hydrogen ion. So if it gained a hydrogen, then I can see that this must be my conjugate acid. Okay. On the other hand, water, if that's the base, water has to be the acid. And remember, because it's amphoteric, it can do both. So it's acting as an acid, which means this must be my conjugate base, which makes sense because if you go backwards, hydroxide is always going to be the base. Okay. All right, let's try letter B. Let's see how you did on letter B. So now I have HOCl. Well, if I check to see what happened to it, it became OCl-, which means it lost the hydrogen. So this must be my acid, and this must be the conjugate base. Now, what happened to this C6H5NH2? Well, I can see that it gained a hydrogen, so it should be my base, and by the process of elimination, it's got to be my base anyway. And so this must be my conjugate acid. And again, if you were to go backwards, you would see that the NH3+ lost the hydrogen, acting as an acid, and turning into a base. Okay. And last one here. So this is what we're talking about when we say that something can be amphiprotic. Okay. And so HSO4- could go in either direction. Okay. Because it could actually turn into SO4 2-, but think about it. It also could have turned into H2SO4 and sulfuric acid. So it can act as both. So this I would call amphiprotic. That I would call amphiprotic, meaning it can go both ways, okay? So in this case, what is it doing? Well, I can see what happened to it is it turned into SO4 2-, which means it lost the hydrogen, must be acting as an acid, which means water must be acting as a base, okay? So then I come over to this side, the acid is connected to a conjugate base, and the base is connected to the conjugate acid. And another tip is H3O+ is going to be an acid, okay? So whether it's a conjugate or an acid, then that's how that would be, okay? Hopefully you're okay with the conjugate acid and conjugate base now. Okay, and finally, just a little bit of something that we already talked about, but just to kind of review this again. So in a way, there's no such thing as a hydrogen ion or a proton without anything else. So they don't exist naked in water solution like that. So remember, water is very polar, okay? And what it means to be polar is it's not ionic, but it's very polar, meaning there's a strong pull in one direction of the electrons. We know that oxygen is a lot more electronegative than hydrogen is. And so what happens is we get a partial negative at the oxygen end and we get a partial positive at the hydrogen end. And so if you see another water molecule that's going to be nearby, we're going to have the same thing where we've got our positive and we've got our negative. And so it creates a dipole moment. And so the dipole is going to be pointing toward the oxygen in both situations. Okay, so in whichever one is more electronegative. Okay. Well, what ends up happening here is we get an attraction where this water molecule will end up attracting this hydrogen ion right here. And when it does that, we actually get the 3 H's with the O, which actually makes our H3O+. And that's our hydronium ion. And then what does it leave behind? Well, it leaves behind our OH, but now it's hydroxide, it's OH-. And so that's how we can get the self-ionization of water. Okay. So it says there's a strong partial negative charge on the side of the oxygen atom, and then there's a strong partial positive charge on the side of the hydrogen. Any loose hydrogen ion having a positive charge would quickly find itself near one of the oxygens of a water molecule. It says at close range from the charge attraction, the hydrogen ion is going to find a pair of unshared electrons, and that's going to be capable of filling that outer shell that it has. We're going to produce our hydronium ion. There it is right there. And the real species that acts as an acid, we've got our little disclaimer here. It says, as we write reactions of acids and bases, it's usually most convenient to ignore the hydronium ion, and instead of writing hydronium, we simply just write H+ instead. Okay. And the last thing I wanted to mention here is don't forget that this is not something that's happening often. When you look at water, if we could actually look inside of a beaker of water at that molecular view of it, we know that our Ka, our Kw for water is actually equal to 1 times 10 to the negative 14. And so when we look at our equation for what is Kw, it's the water as a liquid turning into H plus and OH minus, or hydronium and hydroxide. And we know, sorry, I lost my 1 in there. We know that this means that it's products over reactants, that the number really, really, really favors the reactant side, and the reactant is actually water sticking together as a liquid versus turning into the H plus and the OH minus, or the hydronium ion. So I hope this has helped you. Happy day, everyone, and hopefully you've got a better idea of acids and bases as well as conjugate acids and bases.